So a great way for us to think about muscle is the same way that mathematicians think about muscle when they're, modeling how the muscle produces force. So this is Marcus Pandy, who's one of my favorites in terms of translating, kind of simulated high-end mathematics to clinical practice. And essentially he builds a muscle model here, and you can see the active complements, that sliding filament theory that we talked about earlier, which defines the capacity of a whole muscle in terms of its force length and force velocity relationships. And those are here. And we can kind of see, okay, that's the capacity of this particular muscle, which he's modeling, which is the calf muscles. But he also includes the passive elements. So basically, he doesn't have those drawn in here. So I'm going to draw that in here. So here we would see, here's his resting length, which he's got as 1. And then we know that the passive element of muscle kind of increases like that. So we'll put PE for the passive element. Okay, so here's the active element here, here's the passive element, and this is how it responds to force length changes. Here's how the active element responds to force velocity changes. So we have those here, and he's got those pictures drawn nicely in here. And then the other thing we see is this tendon effect. And so the tendon is in series with the muscle here. So basically we have kind of two effects of connective tissue. One is this stretch that keeps the actin myosin filaments from, over elongating and separating and rupturing the Z bands. That's this passive element here. And then there's also the tendon effect that's in series with this whole unit. So essentially, as I jump up and down or push, there's some stretch in the tendon and recoil in response to this kind of active and passive element interaction. So when we think about muscle, we have to both think about, okay, so in terms of its capacity is what's happening with active and passive elements, and then also what's happening in the tendon. Okay, and then essentially the neural drive, if you can kind of think of a motor unit, this is a motor neuron coming down here, is interacting really exclusively with the active element of the muscle. And that's really why muscle's so complex, because basically we've got the motor unit recruitment and rate coding coming here into the active element. We have the dynamics of the force velocity and force length relationship with the active element. We have the passive elements, which is also interacting with that. And now we're going to add in just a minute the recoil and stretching of the tendon, which is also affecting the force output at the joint. Okay, so let's take a closer look at how neural drive and the active elements help us understand how muscle performs. So essentially what this active elements are telling us here is when we have a 1 here is really the force peak of that particular muscle. And then the 1 on the x-axis tells us what the optimal length is. And so this is our, ideal situation. So if the body wants to produce half of the force peak, it basically can send neural drive, rate coding, and recruitment that's 50% of what its maximum would be, and that'll get it to half, which is right here, which is its goal. But if it was trying to produce that same amount of force at a lengthened position of 40%, so we've 1.4 of 1, at 40% length, we would need now to produce 100% activation, because basically the full capacity of the muscle here needs to be activated to get to that same amount of force. And so that's without taking into account the parallelistic element or the passive element. Okay, so let's do the same thing now for the force velocity curve. So again, we note that the peak force is here at 1, and that 0 on this graph is 0 velocity, so that's an isometric contraction, so that's our peak at that velocity. Okay, and so essentially if the body now wanted to produce 50% of the peak at a 0 velocity, it would need 50% neural drive to get to this level. But then if we have now changed the situation and add a shortening contraction, say at 0.2 relative to its max, 20% of its max shortening, we would need to produce that same amount of force. It would put us here, right? But our peak capacity at that velocity is now just above that 50% point. So we would need about 90% neural drive, just guesstimating, to get to that same force that we got to with 50% neural drive at an isometric contraction.